So now we are still into chapter 2 and we're going to look at resonance. And so we have extensively discussed these bond line drawings. And while they are very good at showing the connectivity of atoms, they do not show where the electrons are because we don't have the lone pairs drawn in. So it's important to remember that the electrons, both bonding and non-bonding, are not static particles. So they behave as clouds of electron density, and that's why we characterize them in orbitals, because it's a cloud. Now, these clouds can spread themselves over large regions of a molecule. And so sometimes, as is shown here with ethylene, and it will become ethylene as soon as I draw those hydrogens in. Okay. We have 2 carbons here with a pi bond, and that pi bond is located between the 2 carbons. So the electrons are localized. Okay. Down here below, where we have this positive charge, the electrons are not localized. So here we can think of the positive charge as a whole, and these electrons, these pi electrons, can move to fill that hole. And when they fill the hole, we get a new hole at carbon 1. So the picture drawn is not an adequate representation of the molecule. And we can look at this molecule, and what we can see, if we look at hybridization first, we can see that carbon 1 is sp2 hybridized. And now you can do this by knowing that it has a double bond, or you can actually calculate the steric number, which equals 3. And if I show you just that quick calculation, carbon 1, okay, here we need to assume that there are 2 hydrogens there, okay, so that carbon 1 has 3 sigma bonds and no lone pairs, so that the steric number equals 3. When we go to carbon 2, there's a hydrogen here, so it's 3 sigma bonds minus no lone pairs, the steric number equals 3. Finally, when we come to carbon 3, it has a positive charge, so it's got to only have 2 hydrogens because it does not have a complete octet. And carbon 3, again, we have 3 sigma bonds, no lone pair, so it has a steric number equal to 3. All 3 carbons have an empty p orbital. And now, if we look at these p orbitals on each of the carbons, what you can see is that they line up. And the electrons can delocalize or spread out across the carbons. So it's a continuous network of p orbitals, and the pi electrons can be spread across all 3 carbon atoms. In order to represent this diffusivity of electron density over regions of a molecule, we need to draw resonance structures for a molecule. And so resonance allows us to use several drawings to represent a single molecule. And we discussed the analogy in class of a peach. And what we said was that a peach, if you were asked a child what a nectarine looks like, we would say that it's in between a peach and a plum. So it's shaped like a peach, and it's often the size of a peach, but it's smooth like a plum. And what's important to note is that a nectarine is always a nectarine. It does not switch forms. And when we look at molecules, okay, a molecule is always the same molecule. The electrons are spread across the entire molecule, but we use different representations to show where the electrons might be and where there might be a region of more electron density versus a region of less electron density. And so if we come down here, that's what this portion of the notes is saying, is that we draw multiple structures to show regions of high electron density and low electron density. So here is an example of the acetate ion. We have a negatively charged oxygen and a neutral oxygen. Well, those lone pairs can delocalize and go between the carbon and the oxygen, and then the pi electrons can be pushed onto the oxygen. So that if you were to look at an electrostatic potential map, you would see that both oxygens have a similar electron density. When we have resonance, it increases the stability of the molecule. So the more contributing resonance structures you can draw, the more stable the molecule. This is very important to remember. Now we can delocalize either a negative or a positive charge, but we have to remember when we draw the representation, we're going to move the electrons. The electrons move. Okay? And so resonance is critical because it shows us, again, where charges are in the molecule. And it also indicates stability. So we are going to use curved arrows to represent resonance and how the electrons move. But again, I need to emphasize that the electrons are not really moving. We are just using this for our minds to reconcile. So we're using multiple structures to reconcile the dispersity of electrons across a molecule. When we draw resonance structures, we're only going to move electrons. So we're looking at pi electrons and lone pairs, or non-bonding electrons. Okay, we're never going to draw an arrow that comes from a positive charge. When we draw curved arrows, okay, let me just dissect the geometry of a curved arrow. So this here is the tail, and the arrow is the head. And the two hooks mean two electrons. So there are certain rules that we have to follow when drawing curved arrows and resonance structures. So we are not going to break any single bonds. So here what this structure is showing you is that you're breaking, when you take the electrons, let me number the carbons, from the bond between carbon 3 and 4, you break that bond. And that is not allowed in drawing resonance. The second rule is we cannot exceed an octet for second row elements. These elements include carbon, nitrogen, oxygen, and fluorine. They only have 4 orbitals in their valence shell, so they can only form 4 bonds. So below, the Skill Builder exercise asks you to identify valid resonance arrows. So if we look at the arrow that's drawn and then draw the structure that it indicates, let me do some numbering here. We can see that the pi electrons between carbons 1 and 2 are moving to be between carbons 3 and 4, and then that will leave a hole on carbon 1. And so this is good. We're not violating any of our resonance rules. So it's not a problem to have fewer than an octet of electrons, but we cannot exceed an octet. If we come down to this structure here with the nitrogen with the amine, my first arrow shows me pushing the lone pair between the nitrogen and the carbon. This violates the octet rule. However, if we then push the pi electrons to the carbon and make a carbanion, we do not violate the octet rule. And what I left out here is that we should have a plus charge on that nitrogen. Now if we look, our starting structure is neutral. So our resonance structure must be neutral as well overall. And that's what's shown here. We have a positive on the nitrogen and a negative on the carbon. If we were to draw resonance structures for nitromethane, again we can see that this negative charge gets dispersed between the 2 oxygens. The positive charge stays on the nitrogen. It's critical in drawing resonance that we indicate these formal charges. Okay? This is where it comes from when we have something that's neutral. It needs to remain neutral overall. So we can generate charges, but they have to be conserved between structures. Okay? Again, these formal charges that we make in resonance structures may not be real, but they show us regions of electron density. So that this here, this carbon might have would have more of a delta minus compared to this carbon out here. And so in drawing resonance structures step by step, we have to keep in mind our 2 rules, that we cannot break single bonds, and we cannot exceed an octet. Okay? And then we have to see, can we convert any lone pairs into pi bonds, any pi bonds into lone pairs, or any pi bonds into new pi bonds. So if we look at this example here, let's draw in our lone pairs. So we have a lone pair on that nitrogen. Well, we can take this lone pair and push it between the carbon and the nitrogen, and then we now have a positive charge on our nitrogen. So this was an example of taking a lone pair into a pi bond. Alright, below here with the oxygen we can convert a pi bond into a lone pair. So if we push the electrons up onto the oxygen, we now have a negative oxygen and a positive carbon. And again, we start with neutral and we remain neutral. So now below here what I have is a series of molecules where we have to figure out if the pairs are valid resonance structures. And there's going to be 1 valid set in each collection of 4 pairs. So if we start over here, okay, we can see 1 and 2, they are not resonance structures because they have a different connectivity. Okay. Now if we look at 2, and I number the carbons here, 1, 2, 1, 2, and let's draw the lone pair in the nitrogen. If we push a pi electron out onto the nitrogen so that we have 2 lone pairs on nitrogen, we generate a negative nitrogen and a positive carbon. So this could be an answer. 3, they are different molecules. Here we have a double bond, here we have no double bonds. 4, if we look at 4, if we were to have a negative charge on oxygen, we would have 3 lone pairs there. Okay. Now if we were to push these electrons down so that we get a carbonyl, we would then have to push those electrons out into the carbon so that there would be a negative charge on that carbon. So 4 is not correct. So our answer is 2. Now let's go to the second set. Okay. Here again, 1, they're not the same molecule. Okay, 2, this time, okay, we push the pi electrons out onto the nitrogen, but we don't have any charge on the carbon. Here for 3, if we were to move these pi electrons, we would generate this structure below. And 4 is incorrect because, again, we are missing the charge down here on the carbon. So 3 is our answer. Okay. So down below here are some more practice examples for you. And that concludes our discussion of our step-by-step drawing of resonance structures.